Welcome, section 8.3. We're talking about the magnetic force of a conductor. And I would like you to remember, all the way from grade 9 science and a little bit from grade 11, electric current is a measure of the amount of charge moving through a wire at a given time. And that tells us that I, for current, is equal to the charge over the change in time. Remember that the current travels through a conductor. And typically we see current traveling through a wire. If the wire is placed in a magnetic field, the moving charge will experience a magnetic force. Okay? And since the charge is in the wire, this magnetic force acts on the wire. So suppose that we have some wire. I'm just going to draw a portion of it out right now. We have some wire and we're going to observe some little section of it and call that L for the length. And we have some charge that is moving through the wire and it is being placed in some magnetic field B. Magnetic field, we have that happening in this case. Recall that the magnetic force on the moving charge is QVB sine theta. And the speed of a charge V is equal to its traveling some length L over some interval T. Let's call this equation double star. Well, let's take our V in this case and substitute it into the first equation as we see here. What that will give us, therefore, is that Fm, my force, will be equal to Q L over delta T B sine theta. But notice this is the same, we can rearrange this a little bit. If we were to rearrange this a little bit, we could have this written as Q over delta T LV sine theta. But Q over delta T is exactly the same as our current. So therefore, the force that is experienced on a wire is equal to I LB sine theta. Which the questions, as we're going to see in a few moments, are fairly straightforward to complete. Similar to the past 2 days, when we're talking about a current carrying conductor, there is a right-hand rule. The basics that you need to know for the right-hand rule for the current carrying conductor is that your fingers will point in the direction of the magnetic field. Your right thumb will point in the direction of the current. The palm of your hand points in the direction of the magnetic force. That is exerted on the wire. So let us go through a fairly straightforward example calculating the force that is exerted on a wire in this case. We have a piece of wire 55 centimeters long, has a current of 10 amps, and the wire moves through a uniform magnetic field of strength 0.37 Tesla. We are going to determine the magnitude of the magnetic force on the wire when the angle between the magnetic field and the wire is 45 degrees. It's fairly easy math when we think about this, because we're given the length of 55 centimeters, which when we divide by 100 is 0.55 meters. We are given our current of 10.0 amps, the field strength of 0.37 Tesla, and the angle of 45 degrees, asking us to calculate the magnitude of the force on the wire. And we simply take everything that we're given and substitute it into the equation. You might notice that I have not written it exactly as ILB. I've written my length first and my current second. Remember, multiplication is commutative, so it can go either way. However, when we do calculate this, couple extra significant digits, we look at our question to see only 2 significant digits are allowed, so therefore the force that's on the wire is 1.4 newtons. And essentially that's it for the lesson for today. I'll be sending out a few practice questions, but that is, we are good to go.